Welcome to our AI for Everyone instructional video series. This instructional video series is developed by the American Institute for Professional Training and Development, a nonprofit organization. This educational video series is designed to provide everyone with an opportunity to learn about AI and explore how to benefit from this remarkable technology. The entire series is available to everyone at no charge. My name is Sandy, and I will be the AI avatar guiding you throughout this presentation. In this video, we will discuss what a neural network is. The term neural network sounds intimidating: brain cells, wiring diagrams, science fiction. We will try to demystify all that. By the end, I hope that you'll feel comfortable explaining a neural network to someone at a dinner party, and you'll appreciate exactly why deep learning took over the world. Let's begin by clearing up 3 things that many people get wrong. First myth: neural networks are like a human brain. In reality, they're loosely inspired by neurons in the human brain, the way planes are inspired by birds, but they work very differently. The second myth: more layers always means smarter AI. In reality, more layers help with complex tasks, but too many can actually hurt performance. It's about the right architecture for the right problem. The third myth: neural networks understand what they're doing. In reality, they just find statistical patterns. Recognizing a cat and understanding what a cat is are 2 very different things. Every neural network is built from a single unit, the artificial neuron. Here's how it works. A neuron receives several inputs. Each input has a weight. Think of it like a volume dial that amplifies or reduces that signal. A strong weight means that the input has more influence on the result. The neuron then sums all the weighted inputs together. The Greek summation symbol you see in the diagram, that's just the mathematical notation for add everything up. Finally, the neuron decides whether it's ready to fire. If the total crosses a threshold, it passes a value forward to the next layer. If not, it stays quiet. Think of this process like a panel of judges scoring a talent performance. Each judge gives a score and input, and some judges carry more influence than others. That is similar to the idea of the weights. If the total score is high enough, the act moves forward. In the case of neurons, it would fire. If not, it's eliminated. Now let's take a look at how a neural network is structured. Imagine connecting thousands of neurons into layers. We will have a neural network. The input layer receives raw data, like pixels in an image, words in a sentence, and numbers in a spreadsheet. Each input node holds one piece of that information. The hidden layers are where the work happens. These neurons detect patterns in the data, edges and textures in the early layers, then shapes and objects, then higher level concepts in later layers. The output layer produces the final answer: an image of a cat or a dog, identifies whether an email is spam or not a spam, or provides a probability score for the result. Think of it like an assembly line. Each station receives partly processed material from the previous one, adds its own transformation, and then passes it along. By the end, the raw input components have become a finished product. Now let's look at how neurons actually learn. There are 4 key terms that power everything inside a neural network, and they're actually simpler than they sound. The first term is weights. Weights are numbers on every connection between neurons. They're what gets adjusted during training. A higher weight means that the connection is more important. The next term is activation function. These functions decide whether or not a neuron fires. After summing up its inputs, the neuron runs a simple math check. If the result is strong enough, it passes a value forward. Otherwise, it stays silent. The third term is backpropagation. This is the learning mechanism. After the network gets an answer wrong, the error signal travels backward through all the layers, nudging each weight slightly so that the next attempt is better. Bias is the fourth term. It is a small extra value that each neuron adds to its sum, giving it flexibility to shift its output even when all inputs are 0. Imagine tuning a music mixing board. Each slider on the board is a weight. Backpropagation is the sound engineer listening to the output. Upon hearing what's wrong, the sound engineer adjusts the sliders, track by track, again and again, until the music mix sounds great. This process is similar to how neurons learn. So, what does the word deep actually mean in deep learning? It just means many hidden layers. A shallow network with one hidden layer can handle simple tasks. A medium network with a few layers can handle more complex ones. A deep network with 10, 50, or even hundreds of layers can learn extraordinarily abstract patterns. Here's why depth matters. Early layers learn low-level features like edges and color gradients in an image. Middle layers combine those into shapes. Deeper layers recognize full objects, faces, or concepts. Each layer literally builds on what the previous one learned. Learning how to read follows the same path. First, you learn letters. Then you learn letter combinations. Then words. Then sentences. Then meaning. Each level of understanding depends on mastering the one below it. The large language models powering ChatGPT, Claude, and Gemini all use transformer architectures with hundreds of layers and billions of connections. That's deep learning in action. Neural networks are already doing remarkable things. Computer vision networks identify objects, faces, and tumors in medical scans. Speech recognition converts your voice to text for Siri and Alexa. Language models like ChatGPT, Claude, and Gemini predict the most useful next word, token by token, through deep transformer layers. Image generators like DALL-E use diffusion networks to create photorealistic images from text descriptions. Self-driving cars fuse signals from cameras, radar, and LiDAR, a remote sensing technology that uses pulsed lasers to measure distances, all function through neural networks. And DeepMind's AlphaFold used neural networks to solve a 50-year problem in biology, predicting how proteins fold in months. That's the power of neural networks in action. Here are 3 key takeaways. Number 1, a neural network is made up of layers of connected nodes, each receiving, weighing, summing, and firing to pass information forward. Number 2, deep just means many hidden layers, and more depth lets a network learn more abstract features. Number 3, what machine learning trains is the weights, not the architecture. The structure is chosen by humans. The weights are learned from data. Thank you for watching. I hope you will join me for the next presentation where we will discuss what deep learning is and why it matters.